So we are going to discuss about compactness in a subspace topology. So let X be a topological space, then Y a subset of X be a topological space, Y subset of X, then Y is compact, if Y is compact in the subspace topology. Y is compact if Y tau Y is compact. Y is compact if it's compact in the subspace topology. If Y tau Y is compact. So we have an important. So what does that mean? For Y to be compact in the subspace topology, that means that every open cover of every open cover of Y, every open cover of Y by sets open in Y has a finite subcover of Y, i.e. every open cover of Y by sets open in Y has a finite subcover of Y. So that's what it means for a subset of X to be compact. But we are going to introduce a powerful condition of this condition. So of this definition, here we have it that every open cover of Y by sets open in Y has a finite subcover. So let us introduce an important condition. So we are going to say let X be a topological space. Let X be a topological space. Y subset of X. Y is compact. Y is compact if and only if Y is compact. If and only if every open cover of Y by sets open in X has a finite subcover. If every open cover of Y, now what are we changing? By definition, Y is compact if every open cover of Y by sets open in Y has a finite subcover. So what are we introducing here? Y is compact if and only if every open cover of Y by sets open in X has a finite subcover of Y. So it's like we need not to worry about the open cover of Y by sets open in Y. We can just look at it as an open cover of Y by sets open in X. So how can we prove this? It's an if and only if statement. So we are going to prove the first direction and then prove the other direction. But what do you have to realize that in the subspace topology, the open sets, I think I commented about this in the last video. The open sets here just tau Y is a collection of open sets of this form. Y intersection W as long as W is open. As long as W is open in X. That's the subspace topology. As long as W is open in X. What are we going to do in that case? What are we going to do in that case? What are we going to do? So suppose that I'm proving the forward direction. Suppose that Y is compact. Suppose that Y is compact. What do we have to show? That every open cover of Y by sets open in X. So let this be, let that be an arbitrarily open cover. Let be an arbitrary open cover of Y by sets open in X. Now we want to show that that thing has a finite subcover. Let that be an arbitrary open cover of Y by sets open in X. What do we realize? That since Y is compact, since Y is compact, now this collection Y intersection W, the collection Y intersection W, whereby W is open in X. Since Y is compact, this collection is an open cover. This is an open cover of Y. It's an open cover of Y, and therefore it's an open cover of Y. It's an open cover of Y. Hence has a finite. This has a finite subcover. Has a finite subcover, which I can call gamma. Has a finite subcover consisting of sets of this form: Y intersection W1, Y intersection W2, up to Y intersection W. Okay. It has a finite subcover. That one has a finite subcover. That one. So what does that mean? That means Y now, if this is the finite subcover of Y is actually equal to the union. Is actually equal to the union of these sets Y intersection I equals 1 up to K. Y is simply the union of that. Now this is equal to Y intersection. I can put this Y outside. Intersection union I equals 1 up to K W I. So we have Y equaling to this intersection. So this means that Y is a subset of I equals 1 K W I. So what does that mean? That simply means that you can easily see it that Y is covered by sets. Y is covered by the union of sets Wi. These W's are open in X. W is open in X. W is open in X. So Y is simply contained in the union, is simply covered in the union of those open sets. So hence W1, W2 up to WK. of wk is a finite subcover of y, is a finite subcover of y. Now we can prove the other direction. We are going to prove the other direction, the converse direction. So suppose that every open cover of y by sets open in X, suppose that every cover y by sets open in X has a finite subcover. So we show that y is compact. So if we want to show that y is compact, we show that y is compact. If we suppose that we want to show that y is compact, by definition, for y to be compact, we have to show that every open cover of y by sets open in y has a finite subcover. So we let an arbitrary open cover of y. So let this, where w alpha is open in X, let this be an arbitrary open cover of y. Now we have to show that that set has a finite subcover. This alpha here is coming from the indexing set. Let that be an arbitrary open cover of y. We show that it has a finite subcover. Now what do we observe in that case? We observe that observe that w equals w alpha coming from the indexing set is what? Is an open cover of y by sets open in X. So we have this collection is an open cover of y by sets open in X, and by our hypothesis, what do we have? We have that every open cover of y by sets open in X. So we have this as an open cover of y by sets. We have that as an open cover of y by sets open in X. So by this hypothesis, w has a finite subcover. So that has a finite subcover. That finite subcover has a finite subcover of y, which I can call gamma, consisting of w1, w2 up to wk. By hypothesis, w has a finite subcover of y, this one. Now we are going to consider y corresponding to each of these sets. So what do we have? We have this as a finite subcover of y. So consider y corresponding to each of those sets. Up to y intersection wk. Consider that. So if we consider that, so this is actually consider consider this collection. Consider this collection, which I can call beta. We realize that beta is a finite subcover, of Y. Hence, Y is compact. Hence, Y is compact. Yeah. So that is the proof of that thing.